Hello, stats class. Here's lesson 7.3b, which is about sample means and probabilities. So I guess it's getting a little predictable lately. We started with sample proportions and their properties, and then we did probabilities in lesson B of 7.2. And then 7.3a was sample means and their the properties of the sampling distribution, and now we're doing probabilities with that. So this actually wraps up the chapter. Last new notes of the chapter. We will review and take a quiz and review more and take a final, and that's about it. So here we go. We talked in 7.3a about if you have small samples, we'll talk about the bad situation first, then the sampling distribution shape is based on the population shape, which means if your population is normal, everything's good, right? If your population is not normal and you have a small sample, then we basically can't do probability calculations. We are not going to learn the more complicated math behind that this year. If you take more stats in college, you might get to it, but we basically are just going to say not enough information to do probability calculations. So we're not going to do that kind. Isn't that great? We're just going to say, sorry, we can't do it. But we are going to do problems where we know it's approximately normal, so therefore we can use the normal distribution. So I'm going to do an example of that. And let's do, this time the variable is the number of texts per day for people that we survey. Let's think about that. The population of that. If I ask everybody in the whole world how many texts per day, there are going to be a lot of people who don't do very many, right? This area over here is going to be very popular, and then there's going to be some outliers way over here who do way too many texts per day. The teenagers are over here, the adults are over here, but I'm just saying most of the world doesn't do a whole lot. So I'm going to say this is a skewed right population. It's kind of a common sense thing, the fact that that happens. That means the mean and the median are different. So maybe the median's about right here and the mean's a little bit further over. And I'm going to tell you that the population mean, let's say it's 15 texts per day. And that's all very nice. Population is skewed right. Here's what we know about the population. It's skewed right, and the mean is 15, and the standard deviation is actually huge, 35. So 35 because this end is so spread out. 30, you can't go one standard deviation below the mean because that's into the negatives, but that's just evidence that it really is skewed right. It's kind of weird because there's this wall at 0 that you can't go past. So this, if I do the if I want to do something like the probability that an individual person X has a number of texts per day greater than 30, there may be some questions in your homework like this where they say find it if you can. And if you have skewed right or skewed anyway, it doesn't matter which way it's skewed, and really small, this is a sample of size 1, I have to say. This is an individual sample of size 1. We can't find this probability. We do not have enough information, and we're not going to learn how to do that this year. So they may ask you that just to see if you're aware that you can't find that. I may ask you that on the next quiz and see if you notice that you can't find it. And some people are still going to get it wrong, and they're going to try to do this normal approximation thing in a z-score. And it's like, no, you can't do that because it's not normal. So because it's not normal, we're like looking at 30, which is way over here, and we're trying to find this little piece. We can't do it because we don't know this formula for this distribution. We're just not going to do that. So if they give you one of those trick questions, please notice it and say to yourself, wait a minute, I can't do that. You can't do it unless it's normal. Okay, so if I really want a normal curve, I need a bigger sample. So let's say, second example, let's say I take this population that's skewed right, and I take an SRS of 50 people. And so then I want to know the probability that the mean of those 50 people's number of texts per day is bigger than 30. Can I do that? Well, let's think about this. How big does the sample have to be for it to be approximately normal? 50. Is that big enough? I hope that you said yes. N is 50. That's bigger than what we said it had to be, which was 30. That's the cutoff for means. That means that my sampling distribution, not my samples or not my population, but my sampling distribution is approximately normal. That's wonderful. That means I can do it. So because the sampling distribution is approximately normal, let's draw a normal curve. And let's say we need to find the mean is the mean of all the x bars. Do you know what the mean of all the x bars is? I hope you do. The mean of all the x bars, this is a mean. Sample means are naturally unbiased, and I did a random sample. Therefore, the mean's the same as this mean. It's still 15. That's amazing. Standard deviation of x bar. Well, it's not 35. It's not the same as the population standard deviation. That's okay. I have a formula. Let's use it. It's this formula that's standard deviation over square root of n. So I'm going to adjust my standard deviation and say because I did big samples, that makes my standard deviation smaller. It's 35 over square root of 50, which you could type in your calculator. I already did, so I'll just write it. I got 4.95 for that. So that means this piece right here is 4.95, and this is 20.95, no, 19, sorry, 0.95, and this is a little bit bigger than 10, 10.05, and I could do that. I could do that. So 30 is way over here. It's going to be a really small probability. That's okay. So in order to do this, because I said it's approximately normal, always check to see if that condition is met. That means I can do a z-score. And I can do 30 minus the mean, which is 15, divided by my new adjusted standard deviation, not the original standard deviation, so 4.95, and that's 15 over 4.95, which is a little bit bigger than 3. Comes out to 3.03. And then I can do the probability of x bar being bigger than 30 is the same as the probability that z is bigger than 3.03, and you know how to do that already. So this probability is the same as this probability. I can find it by doing a normal CDF or looking it up on table A. 3.03 and 999. Notice that, again, it's a greater than, so we're going bigger than 3.03. It's going to be a really, really small probability. And I typed it earlier, so I'll just give that to you, 0.0012, or less than 1% chance. So that's similar to what we did with p-hats. P-hats, you can find the small ones by using binomial formulas. With means, you cannot find it if it's small and skewed, so don't even try, just say, sorry, I can't. But if the sample is bigger than 30, you can use the normal approximation, and you can find a z-score, use these formulas to find the mean and the standard deviation to go in the z-score, and normal CDF. And I will put two more important things. Basically, what I'm doing here, we could write a whole new formula for this. Remember the z-score formula that we had before that was x minus the mean over standard deviation? It's changing a little bit. It is now x bar minus the mean of the x bars over the standard deviation of the x bars, which is the same as saying x bar minus mu, because remember this is the same as the population. And then this one's not the same, it's square root divided by square root of n. We're going to use this formula a lot in later chapters. So we'll write it down now so that we have it for later. And we'll use it now, of course. And then this whole idea, I want to remind you, is based on the central limit theorem that I'm going to write down one more time, because it's so important. The central limit theorem says that as the sample size gets bigger or increases, the shape of the sampling distribution of x bar gets closer to normal. And I think that it's actually true about p-hats also. I can't remember whether this theorem specifically talks about p-hats also, but the same thing happens with p-hat. The shape of the sampling distribution of p-hat also gets closer to normal as sample size increases. So that's the really important theorem about that. We're going to use that to convert things into normal and z-scores as much as possible. So these notes were a little bit short, and that's fine. We are not doing a quiz today because we're going to put it off till next week since we probably need a review. We're going to do a review in the second part of the period. And I'm going to post another video that is my chant because I love it, but I might do it live too also. I think that's it for today, believe it or not, for this lesson. Thank you for listening.